Good morning. Today's lesson is going to be just an introduction to lesson 10.3 and lesson 10.5. Lesson 10.3 and 10.5 kind of go together. If I had written the book, I probably would have put those next to each other instead of having 10.4 in the middle. So we're gonna jump around a little bit. And so we're gonna start off with some terms that are on our tip chart. All right, so you probably never knew this before or had any case to be told this before, but a circle is not the only thing that has a radius. So here's the idea, kind of preview material for lesson 10.3 and 10.5. If you have a regular polygon, so I'm going to make a little sketch of a regular pentagon. If you have a regular polygon, this one's a pentagon. You could have a hexagon or an octagon. That shape can be inscribed in a circle. So a circle could be placed around the pentagon or any regular polygon like this. You can say that the shape is inscribed in the circle or that the circle is circumscribed. That just means drawn around the pentagon. So it looks like this. All right, now you don't have to draw this. I'm just showing you a little background. Okay, so there's a center of the circle, of course. And so since the pentagon is inscribed in the circle, you could say that the pentagon now has a center too. The circle has a center and the pentagon now has a center. And if you connect that center to one of the vertices of the pentagon, then you get a radius of the regular pentagon. So for this lesson and for lesson 10.5, this little intro lesson, shapes that are regular polygons, they have a radius just like a circle has a radius. Now there is a little bit of a difference. A pentagon only has 5 radii. You can put a radius to each one of the vertices, where a circle has infinitely many radii. You could draw a radius right here to the circle, and a radius right here to the circle, and a radius right here to the circle. But a pentagon only has 5. A hexagon has 6, an octagon has 8, like that. So a radius of a regular polygon, it connects the center of the polygon to a vertex. Connects the center of the polygon to a vertex. And so the center of the polygon would be about right here. You can just eyeball that and connect it to a vertex. It doesn't have to be that vertex. It can be any one of the 5, and that is a radius. All right, the next term is probably brand new to you. It's the term apothem. When I first started teaching, I pronounced it apothem, and then some of my teacher friends kind of made fun of me because I was saying it wrong. It's pronounced apothem. And an apothem also starts at the center of a polygon. It connects the center of a polygon to a side of the polygon and is perpendicular to that side. So from the center would be about right there. This is what the apothem is. The apothem is this distance right here. And it's perpendicular to that side. Now, what actually winds up happening, since this radius is the same here, if we were to draw it in, and this radius is the same here, that's actually a perpendicular bisector of that side. So it means that not only is this a right angle, this side is bisected by that apothem. So that's called an apothem. The reason we need that, let me show you real quick. This lesson, I told you this is a preview lesson to 10.3 and 10.5. What we're doing in 10.3 and 10.5 is finding the area of regular polygons. So of polygons like this, or hexagons or octagons? Well, the idea is to divide it into triangles. For a pentagon, there would be 5 of them. For a hexagon, there would be 6. So to find the area of this triangle, since it's 1/2 base times height, we're going to need this base and we're going to need this height right here. Well, you can't call that the height of the polygon. See, the original shape was this polygon. Because that's not the height of the polygon, that's the height of that triangle. And that's what an apothem is. An apothem is the height of one of these triangles that would make up 1/5 of this pentagon. For a hexagon, it would be a triangle that would make up 1/6. Okay. Last term for today is central angle of a regular polygon. Okay, a central angle is an angle formed by 2 consecutive radii. An angle formed by 2 consecutive radii of the polygon. So here's the center again. I'm going to pick out 2 consecutive radii. So that would be radii that are right next to each other. Here's a radius. Here's a radius. So it wouldn't be like this one, this radius, and then this one, or this radius and that one. That would not make a central angle. This is a central angle of the regular polygon. So part of the background of what we're doing today is we're calculating these central angles. And so if we were to draw all 5 of them like I did down here, let me erase this for just a second. If we were to draw all 5 of them, 1, 2, 3, 4, 5, it goes all the way around, makes a full circle. And full circles are 360 degrees. So it'd be pretty easy to calculate what that angle is. You take 360 degrees and you divide it by how many there are. There are 5 of them. And in this case, that would make 72 degrees each. So that central angle is 72 degrees. So that's all for the tip chart for today. And now here is the notes paper. Now we're doing a little intro lesson. Next time you see a video, it'll be over just 10.3, and then the next one will be a video over just 10.5. This is just a little background information for today. So here's the key. All right. So this is what lesson 10.3 is about. It's these 3 shapes in particular. And then this is what lesson 10.5 is about. Lesson 10.5 is about all the rest of them. And so the reason they're separated like that, we could really do them all together. The reason they're separated like that is because these 3, the missing information in the problems, can be found by using special right triangles. And for all the rest of them, these 3 and more, so there are, in theory, infinitely many more shapes that we could talk about that are not these 3. They cannot be solved with special right triangles. You have to use trig for these. All right, so let's do what they're going to ask us to do here. So the idea is to divide the shape into triangles. So I'm going to draw this one kind of dark, like this, and then I'm just going to lightly draw all these. So that you can see that there are 6 of them in a hexagon. And this angle can be calculated like we talked about a minute ago. If you looked at all 6 of them together, that would be 360 degrees. And there are 6 of them, so that is 60 degrees each. So this angle is 60 degrees. That's the central angle. Okay, what we're going to be interested in finding is this apothem right here. That distance, that length. So what happens is that 60 degree central angle, when I drew in that apothem, the 60 degrees got split in half. So that top angle right there is now a 30 degree angle. This is 90, this is 30. That makes this 60. So you can see that we got a special right triangle. So let's say the length was, I don't know, let's say the length was 10. if the side length. So if this whole side length was 10, then this measure that I just pulled out from this triangle right here, this would be 5, and that's across from the 30, and across from the 30 is A. So this is 5. That would make this height right here 5 radical 3. So using a special right triangle, you could pretty quickly find out how long that height is. So you'll see me do this in every single one of the problems in 10.3 and 10.5. I draw that triangle first to calculate that central angle, and then I draw in that height, and I just pull out this little half triangle right here, because this is where we're going to be doing all the work, because this is where the apothem is. The height of that triangle is what we need. Okay, these two are actual special cases. They're going to ask you to do this same kind of work, but since it's a triangle and triangles are the formula is 1/2 base times height, this can oftentimes be done in a shorter method than this current method. And the same thing with a square. A square, you can use base times height. You can use 1/2 diagonal 1 times diagonal 2 because a square is a rhombus. So there's all sorts of other things you can do with a square. But in this lesson, they're asking us to look at it as a regular polygon. So here's the triangle one. It's an equilateral triangle. We know that just because it says regular right here. These are all regular polygons, which means this one's equilateral. Okay, so just like I was doing before, I'm going to calculate that angle, that central angle right there. So you take 360 degrees. You divide it by 3 of them because there are 3 triangles this time. And that gives you 120 degrees for the central angle. And so that's 120. And then when you, sorry, that was my German Shepherd. When you draw in that height, you get this. Get this triangle, and the central angle was 120. The apothem splits that and makes that a 60 and makes that a 30. So we've got a 30-60 triangle again, but it's laying down this time. It's facing a different direction than the one in the hexagon. That's our apothem. Okay, at this point, if you would like to, you could stop the video and do all the rest of them, even the ones down here for lesson 10.5. And then you could start the video again just to check it. And you could, if you're doing well with that, you can just kind of fly through the rest. This is what I'm doing today. I'm just separating out these triangles and calculating that central angle and taking a look at where I would be calculating. I forgot that I was drawing that lower one dark and these light. Anyway, so here's the triangle that I would work in. And here's these, I just draw lighter. Calculating that. You may remember from the rules about diagonals in all the rhombi, including squares, that it makes 90-degree angles. Those diagonals are perpendicular, but if you forget, 360 divided by 4 is 90, and then when you draw in that apothem, that 90 got split in half, and that is now a 45 and a 45. You also may have remembered that in a square, these are all 45s. So you can get there quicker. And here's our apothem. So this one, when you get it all divided up, what shows up is a 45, 45, 90. So let's say this whole side was 10. Well, that's 5. That means that apothem is 5 because it's a 45, 45, 90 triangle. Okay. Now, down here, when we do the same work, when we look at these triangles, you're not going to get special right triangles, which means we are not going to be able to use special right triangle rules to find missing values. So here's our pentagon. We already did this one on our tip chart. We did 360 divided by 5. We got 72. So that's that central angle. So each time you're just dividing 360 by how many triangles there would be, how many central angles there would be here. And so then when we draw in the apothem, And I'm going to take that triangle out right here. So in every regular polygon area problem, you'll see that I'll draw this triangle and I'll pull out that little half triangle there to do the work. This is now 36 because it's half of 72. So see, if I wanted to find this apothem, I'd have to use trigonometry. Normally they give you the side. Sometimes they'll give you radius, but normally they give you the side. Let's say they gave it to us was 10, and this is 5. If that was a 5 right there and the apothem was unknown, I would have to do a tangent problem because this is opposite of the angle and this is adjacent to the angle. So I'd wind up doing a tangent problem to find out what this apothem is. Okay, again, you can pause the video and do the rest if you want to. I'm just gonna finish these up real quick. This one is an octagon. There are 8 of these little triangles. You don't have to draw all of them. You can just draw the one if you want to. And this right here is 360 divided by 8. And 8 goes in there. Let's see, that would be 45. So that angle's 45. Now, that's not a special right triangle because that 45 is going to get split in half by that apothem. So when you draw in this apothem, that 45 gets split, and this one's a weird one. This is a 22.5 degree angle. Okay, last one. So how many does this have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So you do 360 divided by 10. That's an easy one, 36 degrees. That apothem is going to split that 36 degrees in half. Our triangles are getting real skinny. This is 18 degrees. Here's our apothem. So you can see that all the rest of them do not contain special right triangles, 36 degrees, 22.5 degrees, 18 degrees, and so we'll be using trig to find missing values. Okay, so that was a little background of lesson 10.3 and 10.5, and so we'll pick up there in the next lesson when we just look at 10.3. And then the rest of today, there's no homework to do on this. I just want you to spend some time reviewing special right triangles, Pythagorean theorem, trigonometry, vectors for a test on Wednesday. So y'all have a great day. Bye.